here we go for workshop 7. And question 1 involves doing long division and to find out where and how this fraction recurs when you put it in when you go for a decimal expansion. So I will start you off by saying that you should you're going to be dividing 7 into 13. Sorry, 13 into 7. That would not have been a good start. Now, we don't know how many steps you're going to need before it recurs, but you could use as many zeros as you like. Okay? When the remainder repeats, then it recurs. So once you come back to a remainder you've seen before, you can stop because it's going to recur from then on. It doesn't matter which kind of long division you do, whether you go down the page or whether you do compact long division. So whichever your favourite method is, but you should show you're working. Okay? What you can't do is just write down the answer without showing any sort of working at all. At the very least, you should show the remainders as part of compact division. Maybe even show a few other calculations as well. Okay, I'll pause the capture there and we'll see if people can remember how to do long division. Okay, I'm now going to attempt to do the long division myself. This being actual numbers, I could easily go wrong. I'm just like to make mistakes as you. In fact, maybe more likely. But let's see whether I can do it. Right. So I started it off right. 13s into 7 go 0, remainder 7. So you bring the 7 over to 0. You don't have to do that. You could just regard it as 70 in the first place. Then 13s into 70 go 5, remainder 5, because 5 13s is 65. Now I've got to go to 50, where unfortunately we're going to have remainder 11, which is a nuisance. So 3 13s is 39, 50 minus 39 is 11. But if you didn't want to write all that down, I could still deduce what you've done by seeing that you've got the correct remainder. So you can save yourself a bit of effort there. And now we have to figure out how many 13s go into 110. I've forgotten the answer to that, so yes, it's 8 remainder 6. So 8 13 is 104, so 110 minus 104 is 6. So we've got 8 there, remainder 6, 13's into 60, and that's going to be 4, isn't it? Because 4 13s is 52. Giving us remainder 8. And then you've got to go into 80, so that's, what's that one? 6. Giving you 6 times 13 is 78. No calculator in the exam, unfortunately. So we've got remainder 2, and that's going to give us 1, remainder 7. And now, fortunately, we've got a repeat at last. So we now it's just going to be repeating from now on, 5, 3, 8, and so on. And we could stop there. So the answer is 0.5384661 recurring. Any questions about that? Long division. If you don't remember how to do long division, you should learn it. Okay, right. Now, question 2. This is the other way round. This time, you're given a recurring decimal and you're asked to find the fraction, or a form of the fraction. So again, this is a standard technique we did in lectures. but we'll see if people can remember how to do it. Okay? So pause the capture again, and we'll come round. So I started the recording again, and so I'll indicate two methods, because there's the method I did in lectures and a slightly faster method I've just seen someone else use. Okay, so the method from lectures, oh, that's interesting. Not what I meant to do. Computers. Right, so the method from lectures is 1.6172 recurring is equal to 1 plus 0.6172 recurring, and you work this out and add 1 to it, which is fine. And that works, but the method somebody else just used, which I think is slightly faster, thank you very much, is, right, x equals 1.6172, which is equal to 1.6172, 6172, and so on. Then go straight to 10,000x, and you get 16172.6172 recurring. Then you subtract x from that to get 9999x. And the thing you have to remember is you lose the recurring bit and the 1. So you get 16171. So x is equal to 16171 over 9999. And that does seem to be rather quicker than the other way of doing it. If you do it the other way, you get the same answer, but you have to add up one on. You have to add the 1 on in the end, and I think this is quicker. Any questions about? Yes?
I don't understand that step where you do 9999x.
Okay.
How did you minus 1 at time?
Okay. I'm subtracting x. Okay, good. Let's have a look at that in more detail. Okay. So 999x. I want to do 10,000x, take away x, okay? That's 16172.6172 recurring, take away x, which is 1.6172 recurring. So the recurring bit cancels, and you have to take off 1 as well to get you down from 16172 to 16171. Make sense? Good. That's rather nice, actually. Okay. So now you've got two methods of doing it. Is there another question? No. Okay. Right. Okay. So now let's move on to squares, modulo k. We did some squares in the workshop last week as well, so this is just the same. You only ever have to check a few because you know that the others just give you repeats. So if you're working out squares modulo 5, you only have to check 0 squared, 1 squared, 2 squared, 3 squared, and 4 squared, and see what the remainders are modulo 5. But even better than that, because it's squaring, you only have to check 0 squared, 1 squared, and 2 squared, and the rest are repeats again. So we're going to check 0 squared, 1 squared, 2 squared, 3 squared, and 4 squared, but 3 squared is congruent to minus 2 squared is congruent to 2 squared, so that's a repeat, and 4 squared is congruent to minus 1 squared, which is congruent to 1 squared. So, in fact, you only have to check 0 squared, 1 squared, and 2 squared to find the squares modulo 5. And anything else is a repeat of that. Whatever integer you take, no matter what you try, take its square, find the remainder. When you divide by 5, it'll be one of these 3 possible numbers. Okay, so that's that one. Then, having done that, you can go to part B. You have to work out 4th powers modulo 5. Those are the squares of the squares. Okay? So remember, n to the 4th is equal to n squared squared. So you take whatever squares you found in part A and square those and see what you end up with. And you'll find there are even fewer of those than there were squares. There are not very many 4th powers. This is not a coincidence, because hiding behind here is something called Fermat's little theorem, which we don't do in this module, but you will do in the second half of the year. That's why there's so few 4th powers modulo 5. But for now, we'll let you work that out. We'll come around and see if you can work out what you get by squaring or 4th powering these things. Okay, I'm starting the recording again. Okay, so what are the squares and what are the 4th powers? If we could have a little quiet, please, while I run through the answer to this one. So you get 0 squared equals 0, 1 squared equals 1, 2 squared equals 4. So certainly 0, 1 and 4 are squares modulo 5. Everything else is a repeat of those. And all the rest are repeats. Because of what I said up here, but if you weren't sure about that, you could check 3 and 4. Of course, 3 squared you can check directly is 9, is congruent to 4, and 4 squared is 16, is congruent to 1. And everything else is a repeat, because no matter what integer you take, it's congruent to one of these, 0, 1, 2, 3, or 4, and then its square is congruent to the square of that number. So the only squares in here, modulo 5, it's 0, 1, and 4. That's the squares. Any questions about that? Do people know why it doesn't matter why? Suppose you were trying to do something like you were wondering about 997 squared. Why would that just be the same as one of these? Anyone tell me? Suppose you decided to try 997 squared instead. Yeah?
995 squared is congruent to 0, so you still have the congruence of 2 squared.
Yeah, so if you're wondering about 997 squared, whether that might give you something new, 997 is just the same as 2, modulo 5. 997 leaves remainder 2, so 997 squared will leave remainder 4. And that's how it works. That's why you only have to check so few things, and all the rest come as repeats, okay? And that's the beauty of modular arithmetic. So for B, you can either go through and take 4th powers of these numbers, and then you realise that you could just do 4th powers of 0, 1, and 2. Or you can square the squares. We know that the squares are only 0, 1, and 4, so you can square those. Either way, so the 4th powers are squares of squares. So check 0 squared, 1 squared, and 4 squared. Or you can just start from the beginning and look at the 4th powers of these, and you'll realise you only have to check the 4 powers of 0, 1, and 2 anyway. It doesn't. So I haven't saved much time this way. Either way, you get 0 squared equals 0, 1 squared equals 1, and 4 squared is 16 is congruent to 1, mod 5. So if you take 4th powers, you can only get 0 or 1. If you take a 4th power, you cannot leave remainder 2, 3, or 4 modulo 5. And it's not a coincidence that 4 is 5 minus 1. This is from Fermat's little theorem for prime numbers. So if you get interested in why that happened, you'll see it in mathematical structures, I believe. It's not actually a surprise that there's very few 4th powers modulo 5. Okay, so you can only have 0 or 1. Now that's going to be very useful in the next question. Any questions about that? About why there are so few 4th powers? Why we only have to check so few cases? Why are all the other ones repeats? Anybody wondering whether there's some other remainder you could get by trying 2,537 and taking its 4th power? But 2,537 is just the same figure as 2, as far as modulo 5 is concerned. And 2 to the 4 is 16, which is 1. So you don't get anything new. Okay, so now you can use question 4, because if you're working modulo 5, there aren't very many possibilities. So 6 is going to be the same as 1, 7 is going to be the same as 2, 10 is going to be 0, and 9 is going to be 4. So modulo 5, this simplifies quite considerably. Now, there's one thing to watch out for. If you do find a solution modulo 5, it might not be a solution of the original equation. But one thing is for sure, if you find a solution of the original equation, it will also solve it mod 5. So if you can't solve it mod 5, then you can't solve the original equation either. And we've got enough information from question 3 to show that this cannot be solved mod 5, and that's what you're supposed to do here. A little bit of case-by-case analysis. So I'm going to pause the capture and see if people have got some ideas what to try here. You can either do it by contradiction, or just show that there are only a few possibilities for what the left-hand side could be modulo 5, and that they couldn't possibly be 9 or 4. Okay, I'll give you a solution to question 4. So we're going to suppose for contradiction that x, y, and z are integers with 6x to the 4th plus 7y to the 4th plus 10z cubed equals 9. In that case, we're going to get a contradiction from this. Working modulo 5, we have, well, 6 is the same as 1, so that's just x to the 4th. 7 is the same as 2, so this one is 2y to the 4th. Ten z cubed is 0. 10 is 0, so 10z cubed is 0 as well, so we don't need to mention that. And 9 is 4. So that's congruent to 4 mod 5. But we know that x to the fourth is 0 or 1, and y to the fourth is 0 or 1, so 2y to the fourth is 0 or 2, which means we're trying to add 0 or 1 to 0 or 2 and get 4, which doesn't work. So let's see how we might say that. But x to the fourth is congruent to 0 or 1, mod 5. This is by question 3. And 2y to the fourth is congruent to 0 or 2, mod 5. So, 4 cases, x to the fourth plus 2y to the fourth is congruent to 0 or 1 plus 0 or 2. This is slightly informal, mod 5. Very slightly informal, but it saves some writing. That's congruent to 0, 1, 2, or 3, mod 5. And none of those are congruent to 4, mod 5. So this contradicts, let's call this star, that contradicts star. It's not possible. X to the fourth is 0 or 1, 2y to the fourth is 0 or 2. You can't combine those to get 4. So that's it. No solutions mod 5 means there's no solutions at all. If you did find some solutions mod 5, unfortunately that wouldn't be helpful because you wouldn't know whether they solved the original equation or not. You'd have to go back and check. Right. Okay, so that does that one, and so that leaves us with question 5. Oh, sorry. Any questions about that argument? That contradiction shows us no solution, I should say. Okay, so final question is question 5. Just give you a minute to see if a lot of people have already thought about this, but I'll give you another minute if you haven't already thought about it, and I'll just come round and see if people have got ideas for this. A lot of people have found discontinuous functions. Not many people have found a continuous one yet, so I'm going to come round and see how people are getting on. Finish off this question. Okay, let's give you a couple of functions. Lots of people come up with lots of different examples. Here's one way to make a discontinuous example. You come up like this, but you're not allowed to take the value -1, so I put a little round thing there, and I say at that point I'll jump down to -2 and carry on like that. This one is this one here is f of x equals minus x. That's right. It's x minus. What is it? It's x minus 1. I always get this wrong. I don't know why. X minus 1 for x smaller than 0, and it's minus 2 for x greater than 0. And if you check what values it can take, it takes values up to, but excluding minus 1. And then it takes the value minus 2 a lot, but that doesn't change the values you get. Okay, that's a pretty boring discontinuous example. But now suppose you want to get a continuous one. Then you better have an asymptote. One way to get an asymptote to do something like this. And you could use y equals minus e to the x minus 1, or something similar to that. But there's loads of different examples. Okay. So you find your favourite ones. It's good practice to make up some discontinuous ones, because if you're not forced to be continuous, it often makes it a lot easier. You've got a lot more flexibility.